Welcome, just a quick update after spring break. I thought about the problem, this fusion problem. Could not crack it yet, but made some progress. And first of all, it's a very general problem in mathematics that you have two projections and you want to understand the interplay between these two projections. And this is interesting, for example, in statistics, where a projection is nothing else than a data fitting problem. So you have one data fitting problem, you have another data fitting problem, and you want to relate them with each other. And there is some general framework here. We can go from the image of one projection to the image of the second projection. And so we have matrices which we can study, and so there is quite a bit of linear algebra involved. And we can use this statistical framework, of course, this general formula for, call this acute formula for projections, and then we get explicit formulas which self-maps from the images of the projection which we can study. And that's relevant in our case, of the topological case. Now I start to think about it. We have the world G, which is a simplicial complex, and we have a laboratory K, which is a closed subset. And the new thing is that we can also look at the complement, the open set, which is U, and we have a cohomology assigned to U. This, as far as I know, doesn't exist, has not been considered in the continuum. It's here, just linear algebra, because we have concrete matrices both for K and for U. We have an exterior derivative in both cases. So we can look at the Laplacian of the separated system, where we have a Laplacian on the laboratory and a Laplacian on the rest. And we can look at these harmonic forms, which I consider as particles, because physics always looks at round states, the lowest energy configurations, as particles. And then we have also harmonic forms in the whole world, when we don't distinguish between the laboratory and the whole thing. And then so in both cases we have projections, natural projections onto these harmonic forms. This is the kernel of the Laplacian here, which is the image of that projection, and the kernel of the fused, the whole space. Now what happens is, and that's the fusion inequality which I try to prove, is that if you go into the system, where you start separating the system from the rest, what can happen is, we have seen that there can be particles created. For example, I mean, a very simple case is when this is K and this is U, and so on K there is a 1 form, on U there is a 2 form, and they are fused, they disappear when you have the whole thing together. So that's G, when everything is together. And so in this case, the what happened, obviously, if you kind of join the K with the rest of the world, what happens is this harmonic form here on the circle has merged with the harmonic form on the in the interior, has disappeared, and only the 0 form on the circle survives that transition. And of course it has to come in pairs, because the Euler characteristic, what happens is the Euler characteristic of U plus the Euler characteristic of K has to be the Euler characteristic of G. So in this case, the Euler characteristic of U is equal to 1, the Euler characteristic of the K is 0, and the Euler characteristic of the disk, of course, is 1. It's contractible. So this is a kind of a nice prototype situation, where we see that particles, when you are going from the separated system to the world, these particles diffuse away, go away. And when you go from G to U, then particles are created. There's a particle created on the boundary, which is separated now from the interior, and there's a particle in the interior. And these two particles are, and we want to understand what happens using this fusion process. So that's kind of that's the picture. We want to show that when we are going from here to here, we cannot create any particles, new particles. And this is a mathematical problem. It's a linear algebra problem, and I tried to get kind of a grip on that. And what helped a little bit is is a nice article of Anderson Harner and Trapp from 1985, which analyzes this situation of a pair of statisticians who studied a pair of projections. And it's very interesting, and here's the general framework. You have a pair of projections, what you can study. So what you have is you have one space which is onto which you project, and another space onto which you project, and then you want to see what happens when you go from one to the other. So, for example, if you do this S map is a self map now from on V, and this is a self map on W. And so this is in our case, just exactly this is the situation in our case, and we want to show that there is that this space here, this space V, the space when we have separated the laboratory from the rest, that this space V has a larger dimension than this is the laboratory separated system, and this is the joint system. So this is separated and this is joined. So we want to be, when we are joining, we can only lose particles, we cannot win particles. And we can do that analysis. I mean, these Laplacians which we have here, these Hodge Laplacians, they are block diagonal, they leave K forms invariant, and so we can do the analysis. All these analysis can be done for each space of K forms, which is then such a situation. So it's mathematical, it's just a problem of understanding two projections, concrete projections, which are given geometrically. And I still don't know how to prove this, but I can kind of now associate. First of all, I can find some, I wanted to find some kind of Laplacian which gives me this interaction Betty vector, and this can be done. So there is this matrix S here, which is in general not invertible. That kind of measures exactly the amount of new particles which have been created when we go into the separated system. And so T, and that's also equivalent to the claim, is that T is always invertible. So it looks kind of a simple problem, but I still don't know how to attack this. But this paper here is very, very interesting because it relates two matrices. It relates the matrix PQ if you take the product of the two projections, and it relates P minus Q. That's very, very interesting. There's an intimate relation between PQ and P minus Q. For example, the eigenvalues of PQ are directly related to the eigenvalues of P minus Q, and they come in pairs. And then we have also eigenvalues 1 and minus 1. And the eigenvalues 1 and eigenvalues 1 and eigenvalue minus 1 exactly tell how many particles have been created, depending on whether we have more particles on W or we have more particles on V. So this is given by so it's a spectral problem. And so that's actually also a way how I can, alternatively, instead of using, this is actually, if I take this here as an identity, I can define the BI like that, and I can compute that, but I also can compute it by a spectral, by using this, computing this matrix P minus Q, and just look how many eigenvalues 1 I have. And I don't see any eigenvalues minus 1. And that's equivalent. So we have to kind of, it's a basic linear algebra problem. So we have these Laplacians, these two Laplacians, define projections, explicitly given projection matrices. We have the problem to look at P minus Q, look at the spectrum of this P minus Q, and see whether there is an eigenvalue minus 1. The claim is if there is no eigenvalue minus 1, then we are done. And so far I'm still kind of not finished with this, but I think that's one way which looks promising to study this difference between the two projections. And that's it for today.